Ladies and gentlemen, imagine walking out to your driveway, stepping into your Tesla, and discovering that a feature you relied on yesterday is suddenly gone. No warning, no dealership visit, just an overnight update that changes everything. Buyers are stunned, questions are exploding online, and the future of autonomous driving feels uncertain in a single moment. How can a car lose autopilot while you sleep? What does it really mean for safety, for software, and for the future of intelligent vehicles? Stay with me, because what happened overnight isn't just a feature removal. It's a glimpse into how the next generation of mobility truly works. And when customers woke up to the notification that autopilot had been removed from their vehicles overnight, the reaction was immediate. Surprise, confusion, debate. In the connected era of intelligent vehicles, software is not static. It evolves. At Tesla, every vehicle is designed as a continuously improving platform built around real-time data, over-the-air updates, and an uncompromising commitment to safety. An autopilot has always been a driver assistance system, engineered to enhance awareness and reduce fatigue on long journeys. It was never intended to replace the driver. The system relies on neural networks trained on billions of miles of real-world driving data, enabling features like adaptive cruise control, lane centering, traffic-aware adjustments, and intelligent braking. Because the system is software-driven, it can be refined instantly across the global fleet. And in rare circumstances, rapid changes may occur. When data signals the need for immediate calibration, regulatory alignment, or safety optimization, updates can be deployed overnight. This capability is not a flaw. It is the foundation of a modern software-defined vehicle architecture. Unlike traditional automakers that require dealership visits and hardware recalls, Tesla vehicles receive improvements directly through secure wireless updates. That same pipeline can temporarily modify or remove features when necessary to protect customers and maintain compliance. And buyers who invested in autopilot capabilities often see it as more than a feature. It represents a glimpse into the future of mobility, an intelligent co-pilot powered by artificial intelligence. When functionality shifts unexpectedly, it naturally raises questions. Transparency matters. Every adjustment reflects a data-driven decision rooted in safety metrics, performance benchmarks, and real-time fleet analytics. If a behavior pattern emerges that does not meet internal safety thresholds, immediate action is taken. And Tesla vehicles are equipped with advanced camera systems, onboard computing hardware, and proprietary neural network accelerators. The driving stack interprets lane markings, traffic signals, pedestrian movement, and surrounding vehicles through continuous machine learning refinement. When that refinement identifies edge cases requiring rapid recalibration, the system can be updated across millions of vehicles simultaneously. That is the power of centralized AI deployment. And removing or adjusting autopilot overnight does not mean innovation has stopped. It means the system is being recalibrated, validated, or aligned with evolving standards. In some scenarios, regional compliance requirements may change. In others, internal validation cycles may demand temporary suspension of certain behaviors while enhanced models are deployed. Software-defined architecture enables responsible iteration at scale, and Tesla's philosophy has always been rooted in long-term advancement. Hardware installed in vehicles is built with future capability in mind. Many vehicles contain computing capacity designed to support more advanced autonomy than currently enabled. Over-the-air updates unlock, refine, or adjust these capabilities over time. Customers are not purchasing a static product. They are participating in an evolving ecosystem. And the stunned reaction from buyers underscores a larger transformation happening in the automotive industry. Vehicles are no longer mechanical systems frozen at delivery. They are dynamic platforms connected to cloud intelligence. With that connectivity comes agility. Agility means faster safety improvements, accelerated feature enhancements, and the ability to respond instantly to data trends. It also means change can happen overnight, and safety remains the core principle. Internal analytics continuously compare autopilot performance against human driving baselines. Collision avoidance rates, lane departure prevention metrics, and emergency braking response times are tracked in real time. If a deviation from target performance metrics is detected, engineers can deploy corrective updates immediately. That responsiveness reduces risk and strengthens long-term reliability. And buyers expect clarity when changes occur. Communication accompanies updates detailing adjustments and reaffirming that drivers remain responsible and attentive at all times. Driver monitoring systems ensure hands-on awareness and visual engagement with the road. Autopilot is assistance, not autonomy, and its evolution reflects responsible deployment of artificial intelligence in real-world environments. And moments like this highlight the difference between legacy automotive models and a technology-driven approach. Traditional recalls can take months to implement. Software recalls can occur in hours. Overnight modifications demonstrate the flexibility of a vertically integrated software stack. From silicon to neural network architecture, every layer is engineered internally to enable rapid iteration without compromising data security or system integrity. And customers may be surprised, but they are also witnessing the defining characteristic of next-generation mobility: constant improvement. The same system that can be removed or adjusted overnight can also return stronger, more capable, and more refined. Continuous improvement is not a marketing phrase. It is embedded into the vehicle's operating system, cloud infrastructure, and machine learning lifecycle. And Tesla's mission extends beyond building cars. It is about accelerating the transition to intelligent, sustainable transportation. Autopilot is one step in that journey. Its development requires patience, data responsibility, and adaptation. Change, even sudden change, reflects the reality of deploying advanced AI at global scale. And change, even sudden change, reflects the reality of deploying advanced AI at global scale. In a connected fleet operating across diverse road conditions, climates, traffic patterns, and regulatory environments, adaptability is not optional. It is engineered into the foundation of every system. The neural networks powering Autopilot are trained on an ever-expanding dataset that spans highways in North America, dense urban intersections in Europe, and complex traffic flows in Asia-Pacific markets. This diversity strengthens capability, but it also demands continuous validation. And when signals from fleet telemetry indicate an anomaly, even at extremely low occurrence rates, the response cycle begins immediately. Billions of data points are processed through internal simulation environments. Edge cases are reconstructed. Scenarios are replayed at accelerated speeds. Engineers analyze perception outputs, trajectory planning decisions, and control execution. If refinement is required, updated models are compiled, validated in simulation, tested internally, and deployed over the air. The speed of this loop distinguishes a software-defined vehicle platform from legacy automotive systems. An Autopilot's architecture is built on vision-based intelligence. 8 external cameras provide a 360-degree view around the vehicle. High-performance onboard computing interprets that visual data in real time, identifying objects, predicting movement, and calculating safe driving paths. The neural networks evolve through iterative training using real-world examples to improve object recognition, depth estimation, and behavioral prediction. Because the system learns from fleet data, improvements are collective. Each mile driven contributes to refinement across the entire network. And temporary feature adjustments can be part of that refinement. In some cases, parameters may be recalibrated to optimize driver engagement thresholds. In others, certain behaviors may be tuned to ensure smoother interaction with evolving traffic laws or infrastructure variations. Every change is evaluated against rigorous internal benchmarks that measure intervention frequency, driver input requirements, and system confidence levels. If the confidence score does not meet internal standards, deployment pauses until validation confirms readiness. And the expectation of permanence in vehicle features is rooted in traditional automotive manufacturing. However, intelligent vehicles redefine that expectation. The operating system within each vehicle is designed for dynamic capability management. Features can be activated, improved, limited, or reconfigured based on performance analytics. This flexibility enhances long-term value by enabling vehicles to grow more capable over time, rather than depreciating through obsolescence. And security remains central to every update. Over-the-air deployment channels are encrypted end-to-end with multi-layer authentication, ensuring software integrity. Each update package undergoes cryptographic verification before installation. The vehicle's hardware security modules protect against unauthorized access, while preserving user privacy. Data collected from the fleet is anonymized and processed to improve system performance without compromising individual information. And the removal or modification of autopilot functionality can also reflect proactive collaboration with transportation authorities. As regulatory frameworks for advanced driver assistance systems continue to evolve, alignment ensures consistency with global standards. Responsible innovation means working within established guidelines while contributing data that helps shape future policy. Adaptability ensures compliance without requiring physical recalls or hardware retrofits. And customer experience remains a priority. Software notifications provide clarity about system status, while release notes outline performance enhancements and adjustments. Owners retain full control of their vehicles with clear instructions, reinforcing attentive driving practices. Autopilot operates with layered redundancy, visual cues, audible alerts, and torque sensing to maintain driver engagement. The system is designed to assist, not to replace responsibility, and internally continuous improvement cycles operate around the clock. Machine learning engineers refine perception models. Validation teams stress test edge cases. Firmware specialists optimize latency and response times. Every software iteration targets measurable gains in smoothness, predictability, and safety margins. Improvements may not always be visible in a single update, but cumulative refinements create substantial progress over time. And vehicles delivered years ago continue receiving enhancements through this architecture. Processing efficiency increases. Visualization interfaces evolve. Energy optimization algorithms improve range estimation accuracy. This long-term support underscores the philosophy that hardware and software should advance together. The value of a vehicle extends beyond the day it leaves the factory. And moments of sudden change often highlight the complexity behind advanced driver assistance systems. Real-world driving involves unpredictable human behavior, construction zones, weather shifts, and countless variables that cannot be fully replicated in closed testing environments. Deploying artificial intelligence in that environment requires vigilance and humility. Adjustments demonstrate active oversight rather than passive operation. And the broader vision remains consistent. Intelligent systems that reduce fatigue, enhance awareness, and improve overall transportation safety. Each update contributes to a roadmap defined by measurable progress. Fleet learning accelerates development. High-fidelity simulation compresses iteration cycles. Integrated hardware ensures performance scalability. And customers witnessing overnight changes are observing a platform designed for rapid evolution. The ability to refine software instantly across a global fleet represents a structural advantage in safety responsiveness. It transforms vehicles from static machines into adaptive systems. And as data continues to expand and computational capability advances, the intelligence embedded within each vehicle becomes more precise. Lane positioning grows smoother. Traffic response becomes more predictive. Obstacle detection sharpens in complexity. Each iteration builds upon the last, guided by analytics and disciplined engineering standards. And software-defined mobility requires acceptance that progress is iterative. Features are not simply added and forgotten. They are measured, refined, and occasionally rebalanced. Responsiveness ensures that performance targets remain aligned with real-world outcomes. Through centralized architecture and real-time analytics, continuous advancement remains embedded in the lifecycle of every vehicle on the road. And software-defined mobility requires acceptance that progress is iterative. Features are not simply added and forgotten. They are measured, refined, and occasionally rebalanced. Responsiveness ensures that performance targets remain aligned with real-world outcomes. Through centralized architecture and real-time analytics, continuous advancement remains embedded in the lifecycle of every vehicle on the road. And at the core of this approach is a vertically integrated technology stack. From custom-designed silicon to proprietary neural network frameworks, each layer is engineered to operate in harmony. This integration reduces latency between perception and action, enabling faster decision cycles and smoother vehicle control. It also allows rapid deployment of updated inference models without requiring hardware replacement. When improvements are identified, the system architecture supports seamless integration across the fleet. And fleet learning amplifies the impact of every mile driven. Edge cases encountered by one vehicle become training inputs for the entire network. Complex merges, unusual lane markings, temporary construction detours, and rare traffic behaviors are captured, categorized, and incorporated into future model training cycles. This shared intelligence strengthens performance consistency across regions and road types. The scale of this data pipeline enables accelerated iteration, unmatched by traditional testing programs. And simulation environments play an equally critical role. Real-world data is reconstructed within high-fidelity digital replicas of traffic scenarios. These virtual environments allow engineers to evaluate new models under millions of controlled variations before deployment. Weather conditions can be altered instantly. Lighting conditions can shift from daylight to nighttime within seconds. Traffic density can be increased or reduced. By stress testing updates and simulation performance confidence is elevated before software reaches customer vehicles. And when an overnight adjustment occurs, it reflects this comprehensive evaluation framework. Temporary recalibration may reduce certain automated behaviors, while updated neural networks complete validation cycles. This cautious deployment strategy prioritizes measurable safety metrics over feature continuity. It demonstrates that performance integrity outweighs short-term perception. And driver assistance systems operate within clearly defined operational design domains. These boundaries specify the types of road speeds and environmental conditions under which the system performs optimally. As data expands, those domains can evolve. However, until expanded capability meets strict validation criteria, conservative thresholds remain in place. Adjustments ensure the system operates within parameters that meet internal confidence levels. And user interface design reinforces clarity. Visualizations display surrounding vehicles' lane markings and detected objects in real time, enhancing driver awareness. Alerts are calibrated to balance attentiveness without creating distraction. Over time, interface refinements improve clarity and reduce cognitive load. Each software iteration aims to strengthen the collaboration between human driver and machine intelligence. And energy efficiency also intersects with software refinement. Driving algorithms are tuned not only for safety, but for smooth acceleration patterns and regenerative braking optimization. Predictive modeling anticipates traffic flow to minimize unnecessary deceleration and reacceleration cycles. These micro-adjustments contribute to overall range efficiency while maintaining comfort and control stability. And the adaptability of the platform ensures long-term resilience. As road infrastructure evolves to include more advanced signage, smart traffic systems, and connected vehicle communication, the software foundation is prepared to integrate those inputs. Over-the-air capability allows integration without requiring physical modification. Vehicles delivered years earlier remain part of the technological progression. And customer trust is built through transparency and measurable results. Safety reports aggregate anonymized fleet data to illustrate system performance relative to manual driving baselines. These metrics provide insight into collision rates, airbag deployment frequencies, and driver intervention patterns. Continuous publication of such data reinforces accountability and progress tracking. And the stunned reaction to feature changes also highlights a broader cultural shift. Vehicles are transitioning from mechanical products to intelligent devices. Expectations shaped by static ownership models are adapting to dynamic software ecosystems. Just as smartphones receive updates that enhance security and capability, intelligent vehicles evolve through iterative deployment cycles. And this transformation demands robust internal governance. Cross-functional teams evaluate updates from engineering, legal, regulatory, and safety perspectives. Validation protocols include redundancy testing and fail-safe verification. Redundant power systems and backup compute pathways ensure operational continuity, even during updates. Software installation occurs only when vehicles are parked and secure, preserving uninterrupted driving capability. And the neural network stack itself continues to mature. Object detection models become more granular, distinguishing between vehicle types, road debris, and subtle environmental cues. Path planning algorithms grow more predictive, accounting for behavioral tendencies of surrounding drivers. Control modules refine steering smoothness and braking modulation to create more natural driving dynamics. Each advancement emerges from disciplined iteration cycles supported by global data inputs. And artificial intelligence deployed in real-world transportation must operate with humility and caution. Unexpected variables will always exist. Continuous oversight ensures that when patterns shift or rare, anomalies surface, response mechanisms activate without delay. Overnight changes reflect vigilance rather than instability. They demonstrate that active monitoring remains central to deployment. And as computational power advances and neural network efficiency improves, the capacity for deeper perception expands. Future updates will leverage enhanced training architectures, improved sensor fusion techniques, and optimized inference pipelines. Each iteration brings incremental precision to object classification, motion prediction, and environmental interpretation. And customers observing sudden adjustments are witnessing an evolving ecosystem, guided by data and discipline. The platform's ability to adapt rapidly ensures alignment with safety objectives, regulatory landscapes, and performance benchmarks. Through centralized intelligence and fleet-scale analytics, the vehicle remains part of a continuously learning network, advancing with every mile driven and every update deployed. And customers observing sudden adjustments are witnessing an evolving ecosystem, guided by data and discipline. The platform's ability to adapt rapidly ensures alignment with safety objectives, regulatory landscapes, and performance benchmarks. Through centralized intelligence and fleet-scale analytics, the vehicle remains part of a continuously learning network, advancing with every mile driven and every update deployed. And this network operates on a feedback loop measured in hours, not years. Telemetry streams from vehicles contribute to real-time dashboards that monitor perception, confidence, steering, smoothness, braking consistency, and driver engagement frequency. Patterns that once required extended field studies can now be identified almost instantly. When statistical signals deviate from internal targets, investigation begins immediately. That agility defines the operational philosophy behind software-defined transportation. And behind each update is a layered validation process. Raw driving clips are curated and labeled to improve object recognition accuracy. Specialized training clusters process this data at scale, refining neural weights to enhance spatial understanding and motion forecasting. Shadow mode testing allows new models to run silently in the background of active vehicles, comparing their predictions to current production models without influencing control outputs. This comparison generates measurable performance deltas before any change is activated. And only when improvements surpass internal thresholds across multiple categories, collision avoidance, prediction, trajectory stability, and driver intervention reduction, does the updated model advance to staged rollout. Even then, deployment occurs incrementally, beginning with limited segments of the fleet to verify real-world consistency. Gradual scaling protects system integrity and ensures that performance gains translate seamlessly outside simulation environments. And hardware and software synergy strengthens this cycle. The onboard compute architecture is optimized for parallel neural network execution, reducing inference latency to fractions of a second. Dedicated accelerators handle vision processing, while redundant safety controllers supervise system outputs. If unexpected conditions arise, fallback logic maintains baseline vehicle control, preserving driver authority at all times. And Autopilot's development trajectory reflects a measured approach to artificial intelligence integration. Rather than relying on static rule-based systems, the platform emphasizes deep learning models trained on expansive real-world diversity. This methodology allows adaptation to regional driving behaviors, varying signage styles, and complex intersection geometries. Continuous training enhances contextual awareness, enabling smoother merges, more precise lane positioning, and refined speed modulation in changing traffic flows. And energy management algorithms intersect with these improvements. By predicting traffic slowdowns and adjusting throttle inputs proactively, the system reduces abrupt braking events. Regenerative braking calibration evolves to capture maximum efficiency without compromising comfort. Micro-optimizations in acceleration curves contribute to range preservation while maintaining responsiveness. These refinements may appear subtle individually, but collectively they shape a more intelligent and efficient driving experience. And the overnight removal of a feature does not erase years of development. Instead, it underscores the accountability embedded within the system. Software can be paused, recalibrated, and redeployed in response to new insights. That flexibility ensures alignment between technological ambition and measurable safety performance. Responsible scaling of artificial intelligence requires this capacity for recalibration. And driver engagement remains integral to system design. Continuous torque sensing on the steering interface confirms attentiveness. Cabin-facing monitoring systems verify visual focus. Alerts escalate progressively to maintain safe collaboration between human and machine. These safeguards reinforce that advanced driver assistance operates as a partnership rather than a replacement. And as regulatory frameworks mature globally, alignment becomes more dynamic. Standards evolve to reflect growing understanding of AI-driven transportation systems. Over-the-air architecture ensures vehicles remain compliant without physical modification. When guidance shifts, updates can adjust operational parameters swiftly and uniformly across markets. This responsiveness supports harmonized integration within diverse legal environments. And internally, development cycles operate in parallel streams. Perception teams refine visual recognition accuracy. Planning engineers optimize path selection under complex constraints. Control specialists enhance steering smoothness under varying speeds. Safety auditors conduct independent assessments to validate compliance with internal and external benchmarks. Each discipline contributes to a unified objective, incremental advancement grounded in empirical evidence. And the broader transformation underway extends beyond a single feature. It reflects a shift toward adaptive mobility ecosystems where vehicles learn collectively. Data from millions of journeys informs architectural decisions and algorithmic refinements. Centralized intelligence aggregates this knowledge, distributing improvements fleet-wide in compressed timeframes. And technological progress at this scale requires patience and disciplined iteration. Every update is evaluated not only for capability expansion, but for system stability and user clarity. Communication channels within the vehicle interface provide context for changes, ensuring drivers remain informed participants in the evolution of their vehicles. And advancements in computational hardware continue to unlock new possibilities. Increased processing throughput supports more complex neural architectures capable of deeper scene interpretation. Improved memory bandwidth enhances multi-camera fusion, allowing richer environmental modeling. As these capabilities expand, the foundation remains anchored in rigorous testing and measurable performance validation. And the adaptive nature of the platform ensures that vehicles delivered years earlier retain relevance within the innovation curve. Software evolution protects long-term value by preventing technological stagnation. Continuous updates extend capability lifecycles and maintain alignment with current safety insights. And each overnight change, whether temporary or permanent, is part of a disciplined continuum. The system's responsiveness demonstrates active stewardship of advanced driver assistance technology. Through integrated hardware, centralized analytics, and iterative deployment cycles, intelligent mobility advances steadily, shaped by data, guided by safety metrics, and refined through collective learning across the global fleet.